Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020. And this is the second continuation of the mechanical vibrations. And when last we left, you were working on this problem. Maybe you solved it, perhaps not. If you haven't solved it yet, you know what to do. Let's see how you did. Now, the mass and spring constant were already found in the first example, so we don't have to do that work here. But we do need to deal with the dampening coefficient. And to do this, we'll use the formula for the damping force given above with one modification. The original damping force formula was Fd is equal to minus gamma u prime. However, remember that the force and the velocity are always acting in opposite directions. So if the velocity is upward, negative, the force will be downward, positive. And so the minus in the formula will cancel against the minus in the velocity. Likewise, if the velocity is downward, e.g. positive, the force will be upward, e.g. negative, and in this case the minus sign of the formula will cancel against the minus of the force. In other words, we can drop the minus sign in the formula and use the formula Fd is equal to gamma u prime. And they just ignore any signs for the force and velocity. Doing this gives us the following, substituting in the values we have: 12 pounds and 2 is the velocity. We get gamma is 6. So that means we can substitute gamma equals 6 into the equation and we get this. We would multiply all the way through by 2. And we would have this initial value problem to solve. And if we calculate the critical damping, we would see that that's also 6, so we do have critical damping. Now, either from that or otherwise, this means that we solve the differential equation. We're going to get a double root, and the root is going to be d minus 6 whole squared is the operator form, and we're going to get u of t is minus 1/2 e to the minus 6t minus 2t e to the minus 6t. Again, you should be able to come up with this yourself. And here is a sketch of this curve during the first 3 seconds. And you see that the vibration in this system is not really a true vibration as we tend to think of them. In the critical damping case, there isn't going to be a real oscillation about the equilibrium point that we tend to associate with vibrations. The damping in this system is strong enough to force the vibration to die out before it ever really gets a chance to do much in the way of oscillation. Let's look at example 3. Again, the only thing that's changing here is the damper is 17 pounds when the velocity is 2. So you define u of t. You know what to do. Let's see how you did. So we get that gamma, using this equation, gamma is going to be 17 over 2. That's greater than the critical damping. So we have overdamping this time. So we should expect from our theory to get 2 distinct real solutions. And when we substitute this in, this is the initial value problem that we are solving. Multiply all the way through by 2. Now this time the roots are going to be real and unequal. So we get minus 17 over 2 plus or minus the square root of 145 over 2. For graphing purposes, we probably want to change those into decimals, and that's what's been done here. So that means that the solution to this problem is going to be u of t is equal to C1 times e to the minus 2.4 and change t plus C2, and that is e to the minus 14.5 and change t. And when you substitute and find out what C1 and C2 are, you get these values. And so here's a sketch of the displacement in this example. Now, it's interesting to note that even though we are overdamped in this case, it actually takes longer for the vibration to die out than in the critical damping case. That's not always the case, but it is here. Also, notice that, as with the critical damping case, we don't get a vibration in the sense that we usually think of them. Again, the damping is strong enough to force the vibration to die out quick, quietly enough so that we don't see much, if any, oscillation that we would tend to think about with vibrations. All right, let's change the value again of the damper, and this time we're going to have a force of 5 pounds when the velocity is 2. You're to find u of t. You know what to do. Let's see how you did. So this time we are going to be underdamped. It is going to be 2.5, and whenever we use that, 2.5 is the same thing as 5 over 2. This is the differential equation that we have to solve the initial value problem. You should check this, but what you're going to get this time is the roots are going to be minus 5 plus or minus the square root of 119 I over 2. And this time, since they are complex conjugates of one another, we know that the solution is going to be e to the minus 5 over 2 t times this. And if we solve for the initial conditions, we get these as the coefficients for the initial condition. So this is the equation that we are talking about. And if we convert this to a single cosine, as we did in the undamped case, we will square C1 and C2 and take the square root of that, and so we will get that for R. And we will find the ratio of of the constants. The inverse tangent of that is going to be delta 1 or delta 2. Now, as with the undamped case, we can use the coefficients of the cosine and the sine to determine which phase shift we should use. The coefficient of the cosine, C1, is negative, so cosine of delta must also be negative. Likewise, the coefficient of C2, sine, is negative, so sine delta must also be negative. That means that we have to be in quadrant 3, and so it is the second angle that we have, the one up here, for the phase shift. So the displacement then is u of t is equal to that 0.502, etc. That's e to the minus 5 halves t, and it's cosine of this, and that is the phase shift. And you see this time we do get a little bit of oscillation because this is the underdamped case. And we did get a true vibration, and that's the point of critical damping. As we increase the damping coefficient, the critical damping coefficient will be the first one where true oscillation in the displacement will not occur. For all values larger than this, overdamping will not see true oscillation. From a physical standpoint, critical and overdamping is usually preferred to underdamping. Think of shock absorbers in your car. If you hit a bump, you don't want to spend the next few minutes bouncing up and down while the vibration is set up by the bump to die out. You would like to be as little movement as possible. In other words, you want to set up the shock absorbers in your car so as you get the least critical damping that you can to avoid oscillations that will arise from an underdamped case. This lecture will be continued in 23.3.